Welcome to Cambridge IGCSE Physics, Lesson 44.1 Electrical Hazards. Today we explore the dangers associated with electrical systems and how to identify them. Understanding electrical hazards is crucial for safety in both laboratory and everyday situations. This lesson covers core content essential for your Cambridge IGCSE Physics examination. We will examine damaged insulation, overheating cables, and the effects of damp conditions. These concepts are fundamental to electrical safety and appear regularly in examinations. Let's examine our learning objectives for today. By the end of this lesson, you will be able to, first, state hazards of damaged insulation. This means identifying what dangers occur when electrical insulation fails. Second, state hazards of overheating cables. This involves understanding why cables overheat and what risks this creates. Third, state hazards of damp conditions and excess current. This covers how moisture and high currents create dangerous situations. These objectives align with Cambridge IGCSE assessment requirements. The focus is on core knowledge essential for examination success. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, electrical hazards, which means dangers arising from electrical systems and equipment. These include shock, fire, and burns. Second, insulation, which means material that prevents electric current from flowing where it shouldn't. Common insulators include plastic and rubber. Third, overheating, which means excessive temperature rise caused by high electric current flowing through conductors. Fourth, overloading, which means electric current exceeding the safe operating limits of cables or circuits. Understanding these terms precisely is crucial for examination success. Let's explore our first core concept, damaged insulation hazards. The fundamental principle states that insulation prevents dangerous electric current from flowing where it shouldn't. When insulation is damaged, several hazards arise. First, electric shock from exposed conductors. People can receive dangerous shocks by touching bare wires. Second, short circuits causing fires. Current can flow between conductors, creating sparks and heat. Third, equipment damage from current leakage. Electricity flows to unintended locations, damaging sensitive components. Prevention involves regular inspection of cables and immediate replacement of damaged insulation. The diagram illustrates a damaged cable with exposed conductor in the center section. Now we examine overheating cable hazards. This follows Cambridge IGCSE core requirements. The cause is excessive electric current flowing through conductors. When current is too high, cables heat up dangerously. The hazards include, first, fire from melted insulation. High temperatures melt plastic insulation, which can ignite. Second, burns from hot surfaces. People touching overheated cables receive thermal burns. Third, equipment failure from heat damage. Excessive heat destroys electronic components permanently. The power equation is P equals I squared R, where P represents power in watts, I represents current in amperes, and R represents resistance in ohms. Notice how power increases with the square of current. Our third core concept covers damp conditions and excess current. The fundamental problem is that water conducts electricity, unlike pure water, which is an insulator. Tap water contains dissolved salts, making it conductive. The hazards in damp conditions include, first, increased shock risk through water. Electric current flows through moisture on skin more easily. Second, current leakage to earth. Electricity finds alternative paths through water to ground. Third, equipment short circuits. Water creates unwanted connections between conductors. Safety requires never using electrical equipment with wet hands or in damp environments. The diagram shows how current can flow from an electrical outlet through water droplets to earth, creating a dangerous situation. Let's work through our first example. The problem states, a cable rated for 10 amperes carries 15 amperes. Cable resistance is 0.5 ohms. Calculate power dissipated. We are given current I equals 15 amperes, resistance R equals 0.5 ohms. We need to find power dissipated P. Step 1, write the equation. We use P equals I squared R, where P represents power in watts, I represents current in amperes, and R represents resistance in ohms. Step 2, substitute the values. We write P equals 15 amperes squared times 0.5 ohms. Step 3, calculate. 15 squared equals 225 times 0.5 equals 112.5. Step 4. State the answer. The result is 113 watts to three significant figures. This excessive power creates dangerous overheating. Example 2 applies safety analysis principles. The scenario is damaged extension lead in damp garage. This combines multiple hazards requiring systematic assessment. Now we analyze. First, identify exposed conductors. Look for cracked insulation, bare wires, or damaged plugs. These create direct shock hazards. Second, assess moisture levels. Damp conditions increase conductivity and shock risk significantly. Third, evaluate shock risk. Combine conductor exposure with moisture to determine danger level. Fourth, recommend safety action. Immediate disconnection and replacement required. The risk matrix shows our current scenario in the danger zone, high probability and high severity. This demands immediate corrective action to prevent injury or death. Now practice what you've learned with these three questions. Question 1 is basic level. It asks state 2 hazards of damaged cable insulation. Think about what happens when insulation fails to protect conductors. Question 2 is intermediate. It states, explain why overloaded cables become hot. This requires you to apply the power equation and understand energy transfer. Question 3 is advanced. The question is, a 5 ampere fuse protects a 2,300 watt heater at 230 volts. Will the fuse blow? Show calculations. This tests your analytical skills using current and power relationships. For all questions, remember to show you're working clearly, include units in every step, and check your answers make physical sense. Physics principles power electrical safety worldwide. Let's see how today's concepts apply in practice. In home safety, circuit breakers automatically disconnect power when current exceeds safe limits, preventing cable overheating and fires. The physics principle is current detection and automatic switching. In industry, regular cable inspection programs identify damaged insulation before hazards develop. Visual inspection and electrical testing detect deterioration early. In construction, waterproof electrical installations prevent moisture-related hazards. Special enclosures and sealing techniques keep water away from conductors. These applications show why electrical safety knowledge matters. Career-wise, electrical safety expertise leads to many professions. Electrical engineering designs safe systems, safety inspection ensures compliance with regulations, and maintenance prevents hazards through regular servicing. Let's review the solutions. For question 1, the answer is electric shock from exposed conductors and fire from short circuits. These are the two main hazards when insulation fails. For question 2, we explain high current increases power according to P equals 1 squared R, converting electrical energy to heat energy in the conductor. For question 3, we calculate I equals P divided by V equals 2,300 divided by 230 equals 10 amperes. The fuse rating of 5 amperes is less than 10 amperes, so the fuse will blow to protect the circuit. Now, exam success tips. First, always show you're working. Even if the final answer is wrong, you earn marks for correct method. Second, include units in every step of calculation. Third, use command words correctly. State means list facts without explanation. Explain means give reasons using physics principles. Let's summarize today's lesson. The key points to remember are, first, damaged insulation causes shock and fire hazards. When protective material fails, conductors become exposed, creating dangerous situations for people and equipment. Second, overheating cables result from excessive current according to P equals 1 squared R. Power increases with the square of current, so small current increases cause large temperature rises. Third, damp conditions increase conductivity and shock risk. Water allows current to flow through unintended paths, including through human bodies. These three concepts form the foundation for understanding electrical safety. For further study, review electrical safety procedures used in laboratories and homes. Practice power calculations using the equation P equals I squared R. The next lesson covers electrical safety devices, which builds on today's work by examining how fuses, circuit breakers, and earth wires protect against the hazards we've studied.